Okay, let's unpack this. Imagine a machine with the power to both induce profound anesthesia and, potentially cause serious harm or even death. That's the anesthesia workstation. It's an incredible piece of technology, but it demands our utmost respect and understanding. Today, we're diving deep into the intricate world of anesthesia workstations. If you've ever wondered what truly happens behind the scenes in an operating room, or if you're a professional looking to master this critical technology like an elite expert, this deep dive is for you. We're going to give you a shortcut to being truly well informed, ensuring you don't just know what these machines do, but how they do it, and critically, why every detail matters for patient safety.
Exactly. We'll be navigating through the essential systems, exploring everything from gas supply and processing to delivery and disposal. What's fascinating here is how seemingly minor details in design or procedure can have profound impacts on safety. We'll examine the critical role of human vigilance, the evolution of safety features, and the ongoing challenges in ensuring zero harm.
Zero harm. That's a powerful goal, isn't it?
Yeah.
And ambitious. It truly speaks to the immense responsibility inherent in using these machines. When we talk about the anesthesia workstation, we're really discussing a core paradox. Its incredible power comes with inherent peril. These aren't just tools that can malfunction, they are, by their very design, inherently dangerous. They have the power to induce profound anesthesia, but also the power to cause death and serious injury. This isn't about pointing fingers at a machine for a random glitch. It's about acknowledging the immense stakes involved every single time one of these machines is operated.
And that leads directly to a crucial distinction. While actual equipment malfunction is incredibly rare, human misuse and error pose a far greater threat to patient safety. Think about it. It would disturb any of us to read about an untrained driver causing injury or death. So why is it not equally disturbing to learn that some anesthetists, even after electronic self-check routines were introduced, believe the workstation checks itself, or that they feel they were never properly taught how to verify the machine? The stakes couldn't be higher because when errors in gas delivery equipment do occur, the outcome is often mortality or serious morbidity.
It's a sobering thought. This is precisely why organizations like the Anesthesia Patient Safety Foundation, or APSF, exist. Their core mission is absolutely clear: to make sure no patient is harmed by anesthesia. And they pursue this incredibly ambitious goal through what they describe as both educational and motivational means. It's a commitment to continuous learning, to always striving for better, to ensure that everyone operating this equipment is not just familiar, but truly masterful.
However, achieving that mastery is, well, deceptively difficult. And several factors contribute to this challenge. Firstly, each anesthesia workstation model has unique aspects, even those produced by the same manufacturer. What you learn on one model may not transfer well to another. This means you can't just generalize your knowledge. You need specific model-dependent understanding.
Right. Beyond just the sheer diversity of models, what are some of the other practical hurdles for anesthetists trying to achieve this mastery? Are there surprising gaps in training or resources?
Unfortunately, yes. There are significant issues with inadequate training and instructional materials. Anesthetists aren't always available for in-service education within their departments. Continuing education content can sometimes be too limited. And there might not be immediate opportunities to use new equipment soon after a training session. And here's a detail that might surprise you. Instructional materials are often inadequate. For example, only supplying one instruction manual per workstation rather than one per user. How are you supposed to truly master something without personalized resources?
That's a huge oversight, really. And while equipment is designed to meet all legal and technical requirements, the designers aren't always the end users. This means some design limitations are recognized only when the equipment is used clinically, revealing unforeseen challenges. This gap between design and practical application highlights why a deep understanding is so vital. Furthermore, from a legal perspective, users can be held responsible for knowing and following manufacturers' instructions, including checklists and operating manuals. Some courts have even defined deviation from these instructions as prima facie negligence, initial evidence of negligence. This underscores the incredibly high stakes involved for every professional in this field.
So, given this immense complexity and the ever-present risk of human error, how do we actually understand these machines beyond just memorizing components? Is there a better way to approach mastery?
Absolutely. The approach emphasized in leading safety protocols like the 2008 pre-anesthesia checklist is to embrace a systems approach. This promotes a deeper conceptual understanding rather than just rote memorization of individual components. For instance, all workstations share fundamental capabilities. They provide gases, they measure gas composition, oxygen, anesthetic agents, carbon dioxide. Once you understand this overarching capability, it simplifies learning how a particular machine achieves it and how to verify that function safely before use. It's about recognizing those universal principles while still appreciating individual adaptations.
Precisely. And this systems approach extends to powerful mental models like the supply, processing, delivery, and disposal model, or SPDD, and the classification of components into high, intermediate, and low-pressure pneumatic systems. These frameworks are invaluable for appraising equipment and ensuring its safe operation, allowing you to quickly understand the interrelationship of parts regardless of the specific model you're working with. It's like having a universal Rosetta Stone for anesthesia machines.
Diving deeper into that, the SPD model offers a comprehensive framework for understanding how gases move through the anesthesia workstation. It covers everything from their arrival in the operating room to their ultimate disposal. If you picture a diagram, the gas flow generally proceeds from left to right, with a vertical bar separating the internal components, those proximal to the common gas outlet, from the external components that are downstream.
And this model yields some fascinating insights. For example, it clarifies that nitrous oxide and air typically have only one task: direct patient delivery. But oxygen has 5 critical functions within the machine, making it absolutely central to the entire system. The SPDD model also clarifies the similarities and differences between fail-safe and hypoxic guard systems, which we'll delve into, and it makes it clear that the scavenging system, not the patient, is the ultimate destination of waste gases. Oxygen's centrality in this diagram truly reflects its life-sustaining role.
That clarity on oxygen's multiple roles versus other gases' single purpose really helps ground our understanding. Makes you wonder then, are oxygen system failures disproportionately more common or dangerous because of those multiple functions? Beyond the SPD model, components are also classified by the pressure to which they're exposed, which significantly impacts their design and safety implications.
Right. If we connect this to the bigger picture, understanding these 3 distinct pressure systems helps us anticipate where failures might occur and how they might manifest. First, you have the high-pressure system, which is exposed to cylinder pressure. Think about the thick-walled components that handle gas directly from the cylinders, like the hanger yoke where the cylinder connects, the pressure gauge telling you what's in the tank, and the initial regulators that step down that immense pressure. Then there's the intermediate pressure system, exposed to pipeline pressure, typically around 50 psi, which is what the hospital walls deliver. This includes things like the pipeline inlets themselves, check valves that ensure one-way flow, oxygen pressure failure devices, and the flow meter valve that controls the rate of gas. Finally, the low-pressure system is everything downstream from the flow meter needle valve, where the pressure is much lower. This encompasses the glass flow meter tubes themselves, the delicate vaporizers where anesthetic agents are added, any check valves after the vaporizers, and the common gas outlet where the fresh gas mixture exits to the patient. A leak in a high-pressure system, for instance, behaves very differently from one in a low-pressure system, making this classification crucial for troubleshooting and safety.
Knowing those pressure zones really gives you a mental map for the machine. And when we look at the modern workstation landscape, the chapter focuses on current models from major manufacturers like Draeger Medical Think the Apollo, Fabius GS, and Perseus A500, and GE Healthcare with their AZs, Aspire, and Advance models. The key takeaway here, again, is that differences between these models are significant, especially for pre-anesthesia checkout procedures, emphasizing the absolute need for model-specific training. You can't just jump from one to another and assume you know it all.
Indeed. Let's move into the supply section, where we address how gases and electric power arrive at the workstation, and critically, what the likely faults and hazards are.
Starting with pipeline supply, which is really the hospital's lifeline for gases. Oxygen, for example, is produced by the fractional distillation of liquid air, stored at an incredibly cold, negative 160 degrees Celsius, and then converted to gas and delivered to hospital pipelines at a pressure of 50 psi. For safety, hospitals have main and partial area shutoff valves. These are there to isolate sections in case of leaks, interrupt supply during a fire, or allow for repair work.
Systems for nitrous oxide and air are similar. Nitrous oxide arrives at the hospital in large H cylinders connected to a manifold, and then regulators reduce its pressure to the same 50 psi as oxygen and air. So 50 psi is the normal working pressure for the anesthesia workstation. Quick connect couplers on the wall outlets, while convenient because they don't require tools, are a common source of leaks due to their internal springs and O-rings.
And to prevent misconnections, delivery piping for all pipeline gases uses the Diameter Index Safety System, or DIS. This system uses unique sizing and threading for each gas connection, making cross-connection difficult. But here's where it gets really interesting. Despite DIS, cross-connection is difficult but not impossible. We've seen reports, for example, where a nitrous oxide hose was connected to a carbon dioxide wall outlet, leading to brief hypercarbia in a patient, thankfully without lasting complications. It's a testament to the fact that no single safety feature is foolproof, and vigilance is always paramount.
That's a critical point. Supply hoses connect the workstation's pipeline inlets to these wall outlets. At the pipeline inlet, you find a filter to prevent particulate damage and a check valve that ensures unidirectional flow. This check valve prevents gas from leaking out of the workstation if it's running on cylinder supplies and the wall hoses are disconnected.
Now, let's talk about critical pipeline problems, because some of these can be particularly dangerous precisely because they're occult or infrequent. We're talking about issues like pressure loss, excess pressure, the dreaded cross-connection of gas delivery pipelines, contamination leaks, and even the theft of nitrous oxide for recreational use. These aren't just theoretical. Tragically, dozens of deaths in the U.S. have been linked to pipeline problems.
What's truly unsettling about these pipeline incidents, which sadly persist even today, is how consistently they reveal a single, vital truth. No matter how many physical safety features we build in, human factors and a chain of errors can still lead to disaster. We've seen instances where nitrogen tanks were mistakenly delivered with oxygen fittings, or where oxygen lines were purged with nitrogen, leading to patient hypoxemia and even cardiac arrest. The common factor in almost all instances of patient injury from cross-connections has been a failure to use an oxygen analyzer. This is your ultimate truth teller. Until you can prove it wrong, always trust an oxygen analyzer that is reporting low inspired oxygen. It's literally the last line of defense in confirming what's actually flowing to the patient.
And it's not just about the technical systems. The Joint Commission, for example, allows their site visitors to randomly question operating room staff to ensure they are aware of the location and function of pipeline shutoff valves and alarms in their area. This reinforces the human element of knowing your environment and your equipment.
Let's consider one of the most high-priority emergencies: a complete loss of oxygen pipeline pressure. The first indication is the pipeline pressure gauge. If the pressure loss is profound, the oxygen low-pressure alarm, which is a high-priority audible and visible alarm, engages, and crucially, the fail-safe valves halt the delivery of all other gases. Some newer workstations even switch to air to drive the ventilator bellows automatically when oxygen pipeline pressure is lost, which is a significant safety advancement.
Disturbingly, simulation studies shed light on our preparedness for this. Many residents and even specialist anesthetists have been shown to perform poorly in simulated pipeline failures, often failing to identify empty oxygen cylinders or check for backup equipment before induction. They often don't conserve cylinder oxygen effectively or use untested pipeline supplies once pressure is supposedly restored. This points to a persistent challenge in real-world readiness.
So, when facing a complete loss of oxygen pipeline pressure, the management goals are clear. Maintain oxygenation, ventilation, and depth of anesthesia, and confirm a safe oxygen supply. The immediate steps are critical. First, you must trust the oxygen analyzer. Do not attempt to fix it. Second, fully open the E-cylinder of oxygen on the workstation, then disconnect the pipeline. This disconnection is crucial. It prevents flow from the pipeline if it's cross-connected, and it protects the patient from potentially contaminated contents. Plus, it's easier to remember one strategy that's effective for both pressure loss and cross-connection.
Third, ensure the measured FiO2 rises. If it doesn't, you need to ventilate the patient with an ambu bag and room air. Fourth, use low flows of oxygen to conserve your cylinder supply and maintain anesthesia with a volatile agent. Fifth, turn off the mechanical ventilator and ventilate manually through the circle system, because many mechanical ventilators use oxygen as their driving gas, rapidly depleting cylinder supplies. Sixth, call for help, calculate your remaining cylinder time, and call for more cylinders. Seventh, participate in the hospital's disaster plan, which might require prioritizing oxygen for the most critical patients. Eighth, and this is vital, do not reconnect to pipeline gas until it has been tested. And finally, if the circle system is unusable for any reason, ventilate with a freestanding oxygen cylinder or room air via an ambu bag and institute total intravenous anesthesia.
That's a comprehensive protocol, highlighting the many layers of action required. But what about the insidious hazard of cross-connection of gases? This can occur anywhere from the bulk liquid oxygen supply, through the hospital piping, to the wall outlets, hoses, and even the internal circuitry of the anesthesia gas workstation.
Fatalities have been associated with liquid nitrogen being shipped instead of oxygen, carbon dioxide instead of nitrous oxide, and unintentional cross-connections during operating room renovations. Near misses include a nitrogen hose with an air coupler, or nitrogen contamination causing hypoxemia and cardiac arrest. The common factor in almost all instances of patient injury from cross-connections has been a failure to use an oxygen analyzer. In the event of a suspected crossover, you would observe a declining inspired oxygen concentration. The initial actions are very similar to an oxygen pipeline pressure loss. Open the emergency cylinder oxygen supply, disconnect the pipeline, and use low, fresh gas flows with manual ventilation.
And this is the critical point. If the pipeline is not disconnected, its 50 psi pressure will override the cylinder's 45 psi, preventing the cylinder oxygen from flowing even if the cylinder is open. This is a deliberate design feature. The cylinder regulator is set at a slightly lower pressure to prevent silent depletion of the cylinder if it's inadvertently left open after checking. Therefore, disconnecting the pipeline is always a safe and necessary step in any pipeline problem, whether it's pressure loss or a suspected cross-connection, because if the pipeline has pressure, it will prevent your emergency cylinder from delivering gas.
Moving to cylinder supply, these are primarily present on the anesthesia workstation as reserves for emergency use. They should only be open when they are checked or when the pipeline supply is unavailable. Cylinders are labeled, marked, and color-coded, though it's crucial to be aware that color schemes differ internationally. The Pin Index Safety System, or PISS, is another vital safety feature with a unique arrangement of holes and pins that prevents misconnections between the cylinder valve and the yoke. However, this system can be defeated if pins are missing or removed, or if more than one washer is used.
The cylinder valve is the most fragile part of the cylinder and must be protected during transport. It contains safety relief devices, things like a frangible disc that bursts under pressure, a valve that opens at extreme pressure, or a fusible plug made of wood metal that melts at elevated temperatures. These are designed to prevent explosive rupture of the cylinder in case of fire, releasing contents in a controlled fashion.
The hanger yoke serves three functions. It orients the cylinders, provides a gas-tight seal, and ensures unidirectional flow into the machine. It also contains a filter and a unidirectional valve that minimizes transfilling, where gas flows from a higher pressure cylinder to a lower pressure one, which is a potential fire hazard. Regarding cylinder pressure regulators, they convert the high variable cylinder pressure to a constant 45 psi downstream pressure. This intentional pressure difference, slightly less than the pipeline's 50 psi, prevents silent depletion of cylinder contents if a cylinder is inadvertently left open after a check.
That's a really important safety detail that's often overlooked. If a cylinder is left open and the pipeline fails, no alarm will sound at the beginning of the cylinder depletion. A full E-cylinder of oxygen can be depleted in as little as an hour if it's driving a bellows ventilator. The low oxygen supply alarm only signals the end of the supply, not the beginning of the depletion. This is precisely why cylinders should be kept closed after their pressure has been checked.
Cylinder manufacturing, handling, transport, storage, and disposal are regulated by the U.S. Department of Transportation, and industry advisory groups like the Compressed Gas Association and the National Fire Protection Association also set standards. A critical safety point: only non-ferrous or aluminum cylinders may be used in the MRI environment, as steel cylinders have caused fatalities when impacting patients.
It's vital to know and follow the rules for safe handling of cylinders. Always protect the cylinder valve, never stand a cylinder upright without support, and never leave empty cylinders on the workstation. Always remove the plastic cover on the port before installation. Crucially, use only one washer between a cylinder port and the yoke, and never rely only on a cylinder's color for identification. Always read its labeling. And never oil valves. If a yoke is empty, use a yoke plug if available as a backup strategy against check valve failure.
When installing a cylinder, you should check the labels, crack the valve briefly to remove any dirt, pointing it away from yourself and others. Confirm both PISS pins are present and only one washer is used. Place the cylinder in the hanger yoke, check for the absence of an audible leak, and finally, verify the proper gauge pressure.
And if you're ever in an emergency relying on cylinder supplies, you need to know how to calculate how long an oxygen cylinder will last. The formula is simple. Capacity in liters divided by service pressure in psi equals contents remaining in liters divided by gauge pressure in psi. So if an E-cylinder has a service pressure of 1900 psi and a capacity of 660 liters, and your current gauge pressure is 500 psi, you have about 174 liters remaining. At an oxygen flow of 2 liters per minute, that cylinder will last approximately 87 minutes.
It's important to remember this calculation doesn't apply to compressed gases stored as liquids, like nitrous oxide or carbon dioxide. Also, This calculation assumes manual ventilation. Using a mechanical ventilator can consume a minute volume of driving gas each minute, rapidly depleting your supply. Regarding nitrous oxide, it's stored as a liquid, so its cylinder pressure remains at 745 psi until it's more than three-quarters empty, after which it rapidly declines. Change it if the pressure is below 745 psi. Rapid removal, greater than 4 liters per minute, can cause the cylinder to cool and frost. Nitrous oxide is non-flammable but supports combustion, and sadly, anesthesia personnel must be alert to the possibility of its abuse. Medical air is not naturally dry. Hospital compressors actively dry it to prevent equipment damage, and its composition is primarily nitrogen and oxygen.
Now let's talk about the other essential utility, electric power supply. The anesthesia workstation receives power through a single power cord, which can easily become dislodged. Because of this, and the possibility of a main power loss, newer workstations usually have battery backup sufficient for at least 30 minutes of limited operation. However, users must read the operator manuals to know exactly which systems remain powered during that time. Patient monitors, flow meters, vaporizers, and ventilators may or may not continue to function on battery.
Electrical receptacles are often found on the back of the workstation for plugging in monitors. These are protected by circuit breakers or fuses. It's a major error to plug devices that convert electric power into heat into these receptacles, things like air or water warming blankets or intravenous fluid warmers. These devices draw a high amount of amperage, making them more likely to trip a circuit breaker. And if a circuit breaker trips, they're often in non-standard locations, causing valuable time to be lost searching for them.
The consequences of losing main electric power can be significant. Devices like mechanical ventilators, physiologic monitors, room illumination, electronic flow meters, and electronically controlled vaporizers typically require wall outlet power. However, devices such as manual ventilation, mechanical flow meters, laryngoscopes, flashlights, or gravity-controlled infusions do not rely on wall outlet power. Hospitals usually have emergency generators, but they're not completely reliable. There's a documented case of a 90-minute power interruption during cardiopulmonary bypass, complicated by immediate failure of the hospital generators, even leading to personnel injury as they hurried in the dark.
Older workstations experience loss of room illumination, ventilator failure, and electronic monitor failure. Newer machines, with their battery backup, offer about 30 minutes of operation, but typically without patient monitors like ECG or pulse oximetry. Mechanical ventilation may or may not be battery-powered, depending on the model. For instance, the Draeger Apollo provides gas and vapor delivery, mechanical ventilation, and integrated machine monitoring for 30 minutes or more on battery, but patient monitors will not function. Crucially, pneumatic functions like vaporizers, fail-safe systems, and flow meters do remain even after the battery is exhausted. This underscores why it remains critically important to understand and anticipate how each particular anesthesia workstation responds when main electrical power is lost by reviewing its operator manual.
All right, let's transition from supply to processing, where we delve into how the anesthesia workstation prepares gases before delivering them to the patient. It's here we really see the complexity of oxygen's role.
Absolutely. Recall that oxygen has 5 essential tasks within the anesthesia workstation. First, it proceeds to the fresh gas flow meter, acting as a life-sustaining gas. Second, it powers the oxygen flush. Third, it activates fail-safe mechanisms, halting other gas supplies if oxygen pressure drops. Fourth, it activates oxygen low-pressure alarms. And fifth, in many models, it compresses the bellows of mechanical ventilators. In contrast, other gases like nitrous oxide and air typically have only one pathway, through the flow meter to the patient. However, some newer machines can now switch to air as a ventilator-driving gas if oxygen pressure is lost.
That's a fascinating detail about oxygen's 5 tasks. Let's talk about flow meters themselves, which are all about precision control of gas delivery. They have several components: a knob, a needle valve, valve stops, though not always present, a flow tube, and an indicator float. The control knobs are color and touch-coded, so an oxygen flow control knob feels distinct from others. You only need fingertip force to shut off gas flow. Excessive force can damage the needle valve, and flow increases when the knob is turned counterclockwise.
Most current workstations use mechanical needle valves with glass flow tubes, often called Thorpe tubes. These flow tubes are tapered, narrower at the bottom, so they're considered variable orifice flow meters, with the annular opening around the float larger at higher flows. If a gas has 2 tubes, they're connected in series. In the U.S., the oxygen flow tube is traditionally on the right. The Draeger Fabius GS is unique in having its flow meters arranged vertically. Crucially, glass flow tubes are the most fragile part of the machine, susceptible to breakage, leaks as their seals, and inaccuracy due to dirt or static electricity.
Many newer workstations, though, are moving away from glass tubes to electronic flow meters. These capture flows electronically using anemometers or transducers, displaying them numerically with bar graphs. Machines with electronic gas mixers have a backup needle valve and glass flow meter for total fresh gas flow in case of power failure. But with systems like the GE AZs, Avance, or Draeger Perseus, the control is entirely electronic. You select the desired inspired oxygen concentration, the total fresh gas flow, and your carrier gas, nitrous oxide or air, rather than directly controlling individual gas flows with knobs.
For proper care of conventional flow meters, turn them off before connecting pipelines, opening cylinders, or turning on the machine, as the float can shoot to the top and cause damage. Always include them in your visual monitoring sweeps, and never adjust a flow meter without looking at it. And remember to turn off flow meters after each case, especially at the end of the day. Failure to do so can contribute to premature drawing of the carbon dioxide absorbent, hastening its exhaustion and potentially leading to increased degradation of volatile agents, carbon monoxide production, and even canister fires.
Beyond the main flow meters, there are other specialized flow meters. Auxiliary oxygen flow meters, present on most models, are useful for attaching a nasal cannula or simple face mask. Their advantage is that the breathing circuit remains intact for a rapid switch back to the main system, and they provide a readily available oxygen source for an ambu bag. However, a disadvantage is they're tied to the pipeline, making them unusable if pipeline supply fails or is contaminated. Also, you can't easily vary the FiO2, and in head and neck surgery, if not managed carefully, they can pose a fire risk.
Emergency oxygen flow meters are a backup on workstations with electronic gas mixers, supplying wall oxygen to the breathing circuit and vaporizers if the computer or power fails. Then there are scavenging flow meters used on most new machines with open scavenging interfaces. These indicate that suction is adequate, which is mandatory to avoid exposure to waste anesthesia gases. Unfortunately, the suction indicator is often not visible from the operator's normal position. For example, on the Apollo is on the left side of the breathing circuit.
Next up, the oxygen flush, the second task of oxygen in the processing area. This valve delivers a very high flow of 100% oxygen to the breathing circuit, typically between 25 and 75 liters per minute. Its primary purpose is to quickly fill the breathing circuit with oxygen. The flush valve often has a rim to prevent accidental activation, which is critical because activating the flush while the mechanical ventilator is in the inspiratory phase can cause barotrauma. During inspiration, the ventilator relief valve closes, preventing gas from exiting to the scavenger, leading to a rapid pressure buildup in the patient's lungs.
If you need to fill the ventilator bellows quickly, it's recommended to do so with short pulses during the expiratory phase, or simply increase the fresh gas flow to 8 to 10 lemon for a few breaths, which will fill the bellows promptly and without the risk of barotrauma. Remember, the oxygen flush line proceeds directly from the gas supply to the common gas outlet, bypassing the vaporizers. So if you're using it during maintenance, excessive flushing tends to dilute any inhaled agents already established in the breathing circuit, potentially reducing the depth of anesthesia.
Now, let's talk about the layers of protection provided by safety systems for oxygen supply. First, the fail-safe systems. Their purpose is to halt the supply of other gases, like nitrous oxide or air, if oxygen pipeline pressure fails, thereby preventing the patient from receiving a hypoxic gas mixture with less than 21% oxygen. They achieve this through gate-like valves in the non-oxygen gas lines, which are held open by pressure in the oxygen line. If oxygen pressure drops below a set limit, these gates close, either shutting off flow entirely or proportionally decreasing it.
Here's the critical limitation. These fail-safe systems do not analyze oxygen pipeline contents. They are activated only by a pressure drop. This means they do not protect against a cross-connection where the oxygen pipeline pressure is intact but contains the wrong gas. This is a crucial distinction. Fail-safe devices were once also placed in airlines, but newer equipment often only has them in the nitrous oxide line, relying instead on electronic proportioning systems and the ability to use air as a ventilator driving gas if oxygen pressure fails.
Complementing these are low-pressure alarms. Their purpose is simply to signal oxygen pressure loss to the operator. Older systems used a whistle that would sound when pipeline pressure dropped to 28 psi. Newer models use high-priority visual and auditory alarms. As we discussed earlier, knowing the proper response to these alarms during a pipeline pressure loss is absolutely vital.
And then there's the ventilator driving gas. For many anesthesia workstations, oxygen is used to compress the ventilator bellows. For example, the ANAESTHESIA ventilator uses 100% oxygen as its driving gas, which can rapidly consume cylinder oxygen if the pipeline fails.
However, newer models like the A-seats can use either air or oxygen and will switch automatically if oxygen pressure is lost. A significant advancement is the piston or turbine ventilators found in machines like the Draeger, Fabius GS, Apollo, or Perseus. These are electrically powered and do not consume oxygen to drive the bellows. This is a huge advantage as they can operate for much longer on cylinder supplies, which is beneficial in office-based anesthesia or during emergency pipeline loss.
These advancements certainly add layers of safety. But even with all these systems, there's always the potential for a hypoxic mixture. That's where proportioning systems, or hypoxic guards, come in. Their purpose is to prevent the delivery of hypoxic breathing mixtures by linking oxygen and nitrous oxide flows to ensure the final mixture at the common gas outlet is at least 23% to 25% oxygen, a maximum 3-to-1 ratio of nitrous oxide to oxygen.
Examples include pneumatic mechanical systems like the Link 25, used on the Anesthesia and Aspire, where oxygen and nitrous oxide flow control knobs are physically linked by a chain, so oxygen flow automatically increases with nitrous oxide. Newer machines like Draeger's Apollo, Fabius, and Perseus models use electronically controlled systems called Sensitive Oxygen Ratio Controllers, or SORC. This system maintains at least 23% oxygen by limiting nitrous oxide flow and incorporates electronic alarms and a nitrous oxide shutoff.
Despite their sophistication, it's critical to understand that these hypoxic guard systems are not foolproof. They can permit a hypoxic breathing mixture if there's the wrong gas in the oxygen pipeline or cylinder, if the pneumatics or mechanics are defective, if there are leaks downstream of the flow control valves, or if an inert gas like helium is administered, since these systems only link N2O and O2. And here's another subtle but dangerous point. They may not prevent hypoxic mixtures if air, or FiO2 less than 0.30, is administered at very low, fresh gas flows.
This is the unavoidable truth. The proper use of a calibrated oxygen analyzer is always of vital importance to detect a hypoxic mixture. These systems only rely on pressure or ratios. They don't actually analyze the content of the gas being delivered.
And that brings us to the unsung hero, oxygen analysis, the ultimate safeguard. Unlike pressure-based alarms or precautioning systems, inspired oxygen analysis is the only system that truly ensures oxygen is actually present in the pipeline, cylinder, and, most importantly, the patient's breathing circuit. This is why monitoring inspired oxygen is mandatory in every anesthetic.
There are two main sensor types in use today: the electrochemical or galvanic fuel cell, found in models like the Anesthesia, Aspire, and Fabius, and the paramagnetic analyzer, which is in most other models. The paramagnetic analyzer is widely used due to its fast response, low cost, and extremely low maintenance requirements.
Moving on to vaporizers, the devices that precisely control anesthetic depth. Let's briefly touch on the underlying physical principles of vaporization. A vapor is simply the gaseous form of a substance that's a liquid at room temperature. The rate of vaporization depends on the liquid's characteristics, its temperature, and the partial pressure of the vapor. As liquid evaporates, it cools the remaining liquid container because it takes latent heat of vaporization from its surroundings. This cooling would naturally slow down further vaporization.
To counteract this, modern vaporizers employ temperature compensation. They use materials like copper, which has high thermal conductivity and capacity, to transfer environmental heat to the liquid anesthetic, helping stabilize its temperature. They also have built-in devices that direct more gas into the vaporizing chamber if it cools, maintaining a consistent output. It's important to note that the rate of vaporization is not dependent on the ambient pressure of the remaining gases present.
Vaporizers are primarily classified as variable bypass or injector types. Most common are the variable bypass vaporizers, like the Tech 4, 5, or 7, Aladdin, or Vapor 19 and 2000. These work by blending the fresh gas flow from the flow meters with just enough vapor to achieve clinically useful concentrations. Only a small portion of the fresh gas flow, called the carrier gas, enters the vaporizing chamber to pick up anesthetic vapor. The rest bypasses. The ratio of carrier gas to bypass flow is automatically determined by the internal channel resistance. Wicks and baffles ensure full saturation of the carrier gas, which is then diluted with the bypass flow to produce the desired final concentration. These vaporizers are calibrated for concentration and are agent-specific, meaning you can't put one agent in a vaporizer designed for another. They're also out of circuit, meaning not directly in the patient's breathing circuit. The Aladdin vaporizers and the AZs are a step further, being electronically controlled based on inputs from pressure, flow, and temperature sensors.
Less common in North America now are measured flow vaporizers, like the older Vernitrol. These require the operator to manually calculate and set the gas flow through the anesthetic liquid and also manually compensate for temperature changes. While they could use multiple agents, their design was not as inherently safe as modern types, and they are no longer manufactured or serviced in the U.S.
Then there's the Tech 6 injector, which is specific to desflurane and operates on a completely unique principle. It's a heated dual-circuit injector or blender. Crucially, fresh gas flow never passes over the liquid agent. Instead, an appropriate amount of vapor is injected directly into the fresh gas flow. Deflurane is unique because it's near boiling at room temperature and has a very high vapor pressure. If it were placed in a conventional variable bypass vaporizer, it would deliver nearly 100% output, risking a hypoxic mixture. The Tech 6 controls output based on both the concentration dial and a transducer that responds to fresh gas flow. To maintain a known vapor pressure, it's heated to a precise 39 degrees C.
The output of any modern vaporizer can be influenced by extremes of fresh gas flow, extremes of temperature, or back pressure from the breathing circuit and ventilator, often called the pumping effect. However, modern vaporizers are generally more resistant to these effects due to the incorporation of unidirectional valves at the vaporizing chamber inlet or outlet.
When it comes to using vaporizers safely, contemporary models are typically secured in manifolds that hold 2 or 3 units. An interlock system is crucial here, preventing the simultaneous delivery of more than one agent. It ensures only one vaporizer is on, that gas only enters the one that's on, that all vaporizers are locked in to prevent leaks, and that trace vapor output is minimal when a vaporizer is off.
Filling vaporizers can be done with either funnel type or keyed filler systems. Keyed filler types are preferred because they lessen the chance of filling with the wrong agent, although it's still possible. To prevent overfilling, always fill in the normal operating position, watch the liquid level indicator, and critically turn the vaporizer off while filling for variable bypass types. The Tech 6 is unique in that it can be filled while operating, but it's still safer to turn it off momentarily.
There are some interesting model-specific vaporizer features. The Draeger Vapor 19, for instance, has an interlock system and a short-circuit block if removed. There's no check valve between its outlets and the common gas outlet in Draeger machines. The Vapor 2000 is similar but removable by hand and has a unique T transport setting to prevent liquid fouling when tipped. The GE Tech 7 is a variable bypass model designed for less frequent service.
The GE Tech 6 for desflurane is quite distinct. It requires electric power and about a 10-minute warm-up period. It has a status display with indicators for operational, no output with an audible alarm, low agent, warm up, and alarm battery low. If a no output alarm activates during a case due to low agent tilt, power failure, or internal malfunction, you should switch agents without undue delay, considering desflurane's rapid emergence. The Aladdin vaporizers in the GE AZs use cassettes recognized by electronic control and will not deliver agent or nitrous oxide without main power or battery backup and adequate oxygen pressure.
Despite all these design advancements, hazards of contemporary vaporizers still exist. Incorrect agent administration is still possible, even with keyed fillers, emphasizing the need to replace older funnel-type systems. Tipping is hazardous for most vaporizers, causing liquid agent to enter the control assembly, which can lead to unpredictable output and overdose risk. Overfilling is another danger, easily prevented by following manufacturer guidelines.
It's important to remember that reliance on breath-by-breath gas analysis does not replace regular preventive maintenance and calibration for vaporizers. Leaks are relatively common due to malposition, dislodgement, lost gaskets, or mechanical damage, and importantly, these may not be detected by standard checklist procedures. The Tech 6, for example, can leak during filling if the O-ring on the bottle spout is missing. And as vaporizers incorporate more electronics, they become susceptible to electronic failures or unanticipated interactions with other new designs. There are even case reports of Aladdin vaporizers failing due to fresh gas mixer failure or from copious emesis.
These are truly critical points for anyone working with these machines. Let's talk about new agents and low flows and their impact on pharmacokinetics. Wash-in of an anesthetic agent is based on the concept of a time constant, which is simply the capacity, the volume of the breathing circuit, plus the functional residual capacity of the patient, divided by the fresh gas flow. One time constant brings a system 63% of the way to equilibrium, 2 time constants to 86%, and 3 to 95%.
Think of it like our earlier sink analogy. 1,000 milliliter sink with 100 millimin inflow of 1% methylene blue solution will reach 63% equilibrium in 10 minutes. But if you increase the inflow to 500 millimin, that same 63% equilibrium is reached in just 2 minutes. The volume in the sink turns blue faster, not because the concentration changes, but because the rate of inflow is a greater portion of the sink's capacity.
This has significant clinical relevance. During induction, a non-rebreathing or semi-open induction with high fresh gas flow of 5 to 8 element is appropriate for rapid onset of anesthesia and denitrogenation. Using low flows during induction would be extremely prolonged, creating a risk of awareness in the interval between the offset of intravenous induction agents and the onset of action of the volatile agent.
For maintenance, however, low fresh gas flows of 1 to 2 Elman are highly desirable. This conserves volatile agents, increases tracheal heat and humidity, and significantly reduces environmental pollution. But then, for emergence, just like induction, it must occur at higher, non-rebreathing flows to speed the elimination of anesthetic agents and avoid unacceptably prolonged emergence. The manipulation of fresh gas flows across these phases is key to efficient and safe anesthesia.
Now that we've processed the gases, let's move to the delivery phase, focusing on the breathing circuit and ventilation, which is the patient's direct interface with the machine.
The fundamental considerations for all anesthesia breathing circuits are to deliver oxygen and anesthetic agents and to eliminate carbon dioxide. CO2 is removed either by washout with adequate fresh gas flow or by absorption using carbon dioxide absorbent granules. Any breathing circuit creates some resistance to gas flow, and this must be minimized by reducing circuit length, increasing diameter, avoiding sharp bends, and eliminating valves to maintain laminar flow. This is crucial because added resistance is uncomfortable for a conscious patient and can lead to hypoventilation in an anesthetized patient who may not be able to increase their respiratory effort.
One of the defining characteristics of anesthesia circuits is rebreathing of exhaled gases, unlike many ICU ventilators. This rebreathing can be beneficial. Advantages include cost reduction, increased tracheal warmth and humidity, and decreased exposure of operating room personnel to waste gases. The degree of rebreathing increases as fresh gas flow is decreased. While rebreathing exhaled oxygen has no ill effects, rebreathing exhaled nitrogen slows induction. Rebreathing exhaled anesthetic agent during maintenance is desirable for cost and environmental reasons, but rebreathing CO2 is undesirable as it leads to respiratory acidosis.
Dead space is also increased with any respiratory apparatus. Mechanical dead space increases CO2 rebreathing, which is why ventilator tidal volumes are set much larger than spontaneous breaths. In a circle system, dead space ends at the Y piece, the point where inspiratory and expiratory gas streams diverge. It's not increased by longer corrugated hoses. Interestingly, a face mask is associated with greater dead space than an endotracheal tube.
The anesthesia workstation uses dry gases to minimize corrosion and bacterial colonization internally, but providing dry gases to the patient's airway can cause problems. It's common to use passive humidification with heat and moisture exchangers with filtration, or HMEF. Active humidification is less common now because it's less effective at preventing hypothermia than heated air surface warming blankets, and added moisture can clog gas analysis lines, soda lime granules, or flow sensors.
The ability to manipulate the inspired concentration of various components for therapeutic benefit is unique to anesthesia breathing circuits. The concentration set on the dial differs from the concentrations in the breathing circuit, lungs, blood, and brain, and these differences vary over time. The inspired concentration most closely resembles the common gas outlet concentration when rebreathing is minimal, typically at high fresh gas flow. Emergence, importantly, is an active washout process, not just passively waking up.
Breathing circuits are classified based on whether a reservoir breathing bag is present and the degree of rebreathing. Open systems have no reservoir and no rebreathing, like open drop or nasal cannulas. Semi-open systems have a reservoir and no rebreathing if fresh gas flow is greater than minute ventilation, such as a circle system at high flow or non-rebreathing circuits. Semi-closed systems have a reservoir and partial rebreathing, like a circle system at low fresh gas flow. And closed systems have a reservoir and complete rebreathing, which occurs when a circle system uses extremely low fresh gas flow with the APL valve closed, where gas supply precisely matches patient uptake.
Moving to non-rebreathing circuits, like the Mapleson D, which prevents rebreathing because fresh gas fills the corrugated limb during the pause between expiration and inspiration, forcing exhaled gas distally. Common features of these systems include a lack of unidirectional valves and soda lime CO2 absorption. Fresh gas flow determines the amount of rebreathing, and they offer very low resistance and work of breathing. The fresh gas flow required to prevent rebreathing is 2 to 3 times minute ventilation, or a minimum of 5 lumen.
The Bain system is a modified Mapleson D, with the fresh gas hose directed coaxially within the corrugated limb, providing heat and humidity. But here's the hidden danger. Unrecognized kinking or disconnection of this inner fresh gas hose converts the entire corrugated limb into dead space, leading to severe respiratory acidosis and potentially arrhythmias. Users of Bain systems must test the circuit for these problems before use, for instance, with the Pethick test.
The use of non-rebreathing circuits has declined because modern workstations are often not designed for them, and pediatric circle systems are increasingly used instead. While they offer advantages like being lightweight, convenient, and easily sterilized, their disadvantages include the need for high fresh gas flows, which increases cost and pollution, and a greater loss of heat from the patient.
The ubiquitous circle system is the most common breathing circuit in the U.S., primarily because it prevents rebreathing of carbon dioxide while allowing rebreathing of all other gases. It has separate inspiratory and expiratory limbs, and unidirectional valves enforce a flow pattern that directs all exhaled gas through the CO2 absorbent granules. If these valves function and the absorbent is fresh, no CO2 rebreathing occurs.
The APL, adjustable pressure limiting valve, in the circle system creates an adjustable leak during manual ventilation. Its improper setting can lead to pressure buildup. The unidirectional valves are the gatekeepers of clean gas. Their valve leaflets are vulnerable to damage, occlusion, foreign body contamination, or sticking from moisture or absorbent dust, especially the expiratory valve. This highlights why daily pre-anesthesia checklists and regular maintenance are crucial. If inspired CO2 is greater than 3 mmHg on the capnograph and increasing fresh gas flow to 5 to 8 mm doesn't resolve it, suspect valve incompetence. An incompetent valve turns the entire corrugated limb into dead space.
It is mandatory to check unidirectional valves before use. One suggested method is to place a spare breathing bag on the Y-piece, then mechanically ventilate this artificial lung, observing that the valves lift and fall correctly and gas flows tidily. Automated checks, however, do not reliably detect breathing circuit obstruction from foreign bodies or stuck valves. This is a critical human check that must always be done.
The advantages of the circle system include constant inspired concentrations, conservation of heat and humidity, minimal OR and environmental pollution, and low resistance. Its disadvantages include its complexity, opportunities for misconnection, and the serious problems caused by malfunctioning valves. Modern circle systems have features that facilitate low-flow anesthesia, such as compliance and leak testing, fresh gas compensation, and low-volume, less leaky absorber heads, which lead to shorter time constants and faster changes in inspired concentration.
However, there are circumstances when you absolutely must avoid low fresh gas flows, specifically less than 1 mmin. Absolute contraindications include patients with smoke inhalation injury, malignant hyperthermia, or conditions where high oxygen uptake is expected. If equipment breaks down mid-case, like an oxygen or agent monitor or the soda lime fails, you also need to switch to higher flows. Relative contraindications include older, less leak-proof equipment, face mask anesthesia, rigid bronchoscopy, or uncuffed endotracheal tubes.
Humidification and infection control are also vital. Heat and moisture exchangers with filtration, or HMEFs, are common, precipitating exhaled water and returning moisture, while also providing bacterial and viral filtration. Cleaning the bellows is necessary after airborne or oral secretion diseases. The American Association of Nurse Anesthetists, or ANA, standards emphasize safety precautions for patient, provider, and staff, acknowledging that equipment and providers become contaminated. Mandatory cleaning and sterilization, good housekeeping, and universal precautions are essential, following manufacturer's directions.
Now, let's talk about carbon dioxide absorption, the very heart of the circle system. It's what makes rebreathing exhaled gases possible, which in turn conserves agent, oxygen, nitrous oxide, and tracheal humidity, all while preventing the respiratory acidosis that would otherwise result from rebreathing CO2. The chemistry of soda lime involves ionic reactions on the granule surface in an aqueous medium, and its water content, typically 10–20%, is crucial for the speed and efficiency of these reactions. Dry granules exhaust much faster.
Activators like NaOH and KOH are added to increase reaction speed, though KOH has been implicated in the production of carbon monoxide and compound A from anesthetic degradation. Notably, 1 mole of CO2 absorbed produces 13,000 kilocalories of heat. Ethyl violet is the indicator, changing from colorless to blue-purple at a pH of 10.3 as the absorbent becomes exhausted.
A critical point about soda lime. It does not regenerate its CO2 absorption capacity during periods of rest. While it might exhibit some color reversion changing back from blue-purple to white during a rest period, this means the color at the beginning of the day is unreliable as an indicator of remaining capacity. You must judge the degree of color change at the end of each case and change the canister if necessary before the next one.
The main constituent of most absorbents is calcium hydroxide, with holders like silica. Granule size is typically 4 to 8 mesh, a compromise between resistance to flow and absorption efficiency. Larger granules mean less resistance but are less efficient. A significant concern is agent degradation and byproducts.
Sevoflurane, for instance, can degrade into compound A, which is lethal in rats at certain concentrations and can cause renal injury. While clinical human nephrotoxicity hasn't been shown despite millions of anesthetics, compound A concentrations achievable in practice at extremely low fresh gas flows are a concern. Desflurane and isoflurane, in contrast, can degrade into carbon monoxide, especially with dry absorbent and strong bases like KOH.
So the recommendations for safe use of absorbents are crucial. Use those with lower or no strong bases. Prevent desiccation by turning off gas flow when not in use. Change absorbent regularly, for example every Monday, and change it whenever inspired CO2 reaches 3 mmHg or the color changes. Always change all absorbent, not just one canister in a dual system, and change if hydration is uncertain. Low fresh gas flows during procedures also help keep granules moist.
Newer innovations in absorbents include those with lower or no strong bases. Many traditional soda-lime absorbents have been modified to reduce NaOH and eliminate KOH. There are also absorbents totally lacking strong bases, like Amsorb Plus, Litholyme, and Spirolith. These offer similar efficiency to soda-lime but avoid compound A or carbon monoxide generation, even if desiccated. Litholyme, for example, uses lithium chloride as a catalyst, preventing degradation and color reversion. Spirolith, a powder in a polymer sheet, is unique because its water content is chemically bound, preventing desiccation, but it lacks a color indicator, requiring inspired CO2 monitoring.
In practical terms, the resistance of filled absorbent canisters is low, less than an endotracheal tube. Inhaled dust from strong base absorbents can be caustic and irritating. When pressurizing the circuit for checkout, releasing pressure through the APL valve rather than the Y piece propels dust toward the scavenger and also checks APL function.
Absorbent efficiency can be reduced by channeling and the wall effect, where exhaled gas follows low-resistance pathways through the canister, exhausting capacity prematurely. Shaking the canister before installation helps prevent this. And critically, ensure the canister is without cracks and properly locked, as cracks or malposition can lead to large leaks and have even been reported to cause canisters to explode.
Recognizing exhaustion and replacement of canisters is vital. Clinical signs of exhaustion include an increase in end-tidal CO2 and inspired CO2, respiratory acidosis, hyperventilation, and signs of sympathetic activation like flushing or cardiac irregularities. Later signs include changes in heart rate and blood pressure and dysrhythmias. But remember, some signs may be masked in an anesthetized patient. Increased FICO2 and absorbent color change are the primary indicators. However, it's unwise to rely on color change or canister temperature alone, as color reversion can give a false sense of remaining capacity.
When replacing canisters, wear goggles and gloves and a mask if pouring loose absorbent. Note the purple color or last change date. For dual systems, place the new canister on the bottom and the old bottom canister on top. Now here's a crucial caution. Do not change ANAESTHESIA-style dual canisters or loose fill in mid-case, and be hesitant to change any canister mid-case. Problems with delayed ventilation continue to be reported with mid-case changes. If granules become exhausted mid-case, the safer alternative is to increase fresh gas flow to 1 to 2 times the minute ventilation to reduce CO2. Change the granules after the case.
Each canister in an Anesthesia-style dual absorber contains about 1.1 kilograms of granules, with a theoretical capacity to absorb up to 15 liters of CO2 per 100 gram. While an adult produces 12-18 LNHR of CO2, the clinical longevity of these large canisters is much longer than theoretical, often 67 to 79 hours or more with typical fresh gas flows, because higher flows dilute exhaled CO2 and wash it out. Manufacturers often recommend changing absorbent if it's left in the machine for longer than 48 hours or weekly, even if unused, due to indicator inactivation and desiccation if gas flows were left on. A proposed threshold for changing due to exhaustion is an inspired CO2 of 3 mmHg.
Now let's talk about ventilators, the breathing machine within the machine. Modern ventilators, whether gas-driven bellows or piston-driven, are multi-mode, double-circuit, electronically controlled, and volume or pressure limited. They cannot operate without power or battery backup.
Gas-driven bellows ventilators are often described as a bag in a bottle. Compressed gas, either oxygen or air, acts as a driving mechanism to compress the bellows, which then propels gas into the patient's lungs. The patient's gases are contained within the bellows, separate from the driving gas. Leaks in the bellows can cause dilution or loss of agent or oxygen. The ventilator relief valve, also known as the spill valve or overflow valve, maintains circuit volume and pressure by releasing gas to the scavenger in an amount equal to the fresh gas flow. This valve opens only during the expiratory phase. A small weight in the relief valve creates 2 to 3 centimeter H2O of PEEP, positive end expiratory pressure, which is inherent to the design of standing bellows.
Piston-driven ventilators, found in models like the Fabius GS and Apollo, use an electric motor to compress gas in a rigid piston. Crucially, they do not consume driving gas, meaning they won't deplete the oxygen cylinder if the pipeline fails. They are quiet and have no inherent peep. They offer great precision and deliver tidal volume due to compliance and leak compensation, fresh gas decoupling, and their rigid design. Disconnects are detected by low-pressure alarms, capnography, and the visible movement of the manual breathing bag, which inflates during inspiration as fresh gas flow is diverted. These ventilators also have positive and negative pressure relief valves built in.
The piston design does have some disadvantages. It doesn't display the characteristic motions of a standing bellows during disconnects, and it's quieter, making it harder to hear its regular cycling. It also cannot easily accommodate non-rebreathing circuits. A newer innovation is the turbine ventilator, like in the Draeger Perseus A500. A spinning impeller generates inspiratory flow, and unlike other Draeger models, the manual breathing bag compresses during inspiration. These allow for faster gas concentration changes.
Modern ventilators incorporate a variety of typical ventilator alarms, including pressure alarms, high subatmospheric, volume alarms, low tidal or minute, rate alarms, high respiratory rate, and reverse flow alarms, indicating an incompetent expiratory unidirectional valve. A key safety feature is that apnea or disconnect alarms are enabled with the first breath sensed. However, alarm fatigue is a significant safety issue, and audible alarms should never be silenced permanently in routine circumstances.
Regarding ventilator modes and settings, modern ventilators offer unprecedented tidal volume accuracy due to electronic compliance and leak testing and compensation for fresh gas flow changes. This means less need to switch to non-rebreathing circuits for small children, which increases safety. The proliferation of modes and controls offers flexibility, but also adds complexity and a learning burden for the operator.
There's been a significant re-examination of intraoperative ventilation, particularly with protective or open lung ventilation strategies, driven by concerns about lung injury and the use of anesthesia workstations for critically ill patients during the COVID-19 pandemic. The goals of protective ventilation include preventing volley trauma, keeping tidal volume to 5 to 7 millibaric predicted body weight, barotrauma, PIP less than 35 centimeter H2O, plateau pressure less than 28 centimeter H2O, driving pressure less than 16 centimeter H2O, minimizing atelectasis, and avoiding hyperoxemia.
All ventilators offer volume-controlled ventilation, VCV. In this mode, the desired tidal volume is delivered at a constant flow. It's volume-limited, time-cycled, and constant flow, and inspiration terminates when the desired tidal volume is delivered or if excessive pressure is reached. The benefit is that alveolar ventilation and arterial CO2 can be maintained despite changes in pulmonary function. However, the peak inspiratory pressure is uncontrolled and will rise with decreased compliance or increased resistance.
Pressure-controlled ventilation, PCV, on the other hand, limits the peak inspiratory pressure and uses a decelerating flow pattern, where inspiratory flow is strongest early in inspiration. This pattern increases lung inflation and oxygenation at the lowest PIP, though the increase in mean airway pressure can decrease venous return. The limitation here is that tidal volume is uncontrolled and varies with compliance or resistance. PCD is indicated when high inspiratory pressure is dangerous, for example, with an LMA, emphysema, or neonates, or in patients with low compliance, pregnancy, laparoscopy, obesity, ARDS, or to compensate for leaks.
For spontaneously breathing patients, especially those with LMAs or undergoing short procedures, synchronized intermittent mandatory ventilation, SIMV, is often used. This delivers mandatory breaths in synchrony with the patient's spontaneous efforts. You can adjust the trigger window and sensitivity to optimize the synchrony.
To address the problem of variable tidal volume in PCV, pressure-controlled ventilation with volume guarantee, PCVVG, also known as autoflow on Draeger models, was developed. This combines the benefits of PCV with assured volume delivery by dynamically adjusting the inspiratory pressure to deliver the target tidal volume using the lowest possible pressure.
Pressure support ventilation, PSV, is another pressure-controlled mode, but with a respiratory rate of 0. It's responsive to patient efforts, augmenting tidal volume during maintenance or emergence. It's useful for denitrogenation and can have apnea backup. Finally, CPAP, continuous positive airway pressure, BiPAP, bilevel positive airway pressure, and PEEP, positive end expiratory pressure, are crucial for maintaining lung volume and oxygenation. CPAP increases intrathoracic pressure and prevents collapse, but does not ensure alveolar ventilation. BiPAP, with distinct high and low pressure settings, can maintain adequate minute ventilation even without patient effort. Modern ventilators integrate electronic PEEP, which is safer than older add-on adapters that could cause obstruction if misplaced.
It's important to learn from critical incidents related to ventilation. The underlying causes of all critical incidents often trace back to improper or infrequent maintenance, inadequate in-service education, substandard monitoring, failure to check equipment before use, and a general lack of familiarity with equipment standards.
Failure to ventilate is arguably the most common preventable mishap. Disconnection is the leading cause, most often at the Y piece, but leaks from improper reassembly, defective canisters, switch failures, or even inadvertent suction can also cause it. Vigilance is key. Continuous auscultation of breath sounds and direct visual observation of chest movement are primary monitoring methods. Electronic monitors are secondary but essential. However, alarms can be disabled or lead to alarm fatigue, so there's no substitute for the anesthetist's five senses.
To manage an inability to ventilate due to low pressure, first check breath sounds. If not ventilating, check for disconnects and try manual ventilation with the anesthesia breathing circuit to continue agents. If initial assessments fail quickly, switch to manual ventilation with a backup ambu bag and institute total intravenous anesthesia. Do not interrupt ventilation for diagnosis. While modern workstations reduce the risk of failure to initiate or resume ventilation with their centralized data, prioritized alarms, and electronic checklists, human factors like lack of knowledge or failure to use checklists persist.
Barotrauma and high pressure in the breathing circuit can evolve quickly with devastating consequences, rapidly impeding venous return and cardiac output. Causes include obstruction to exhalation, such as direct wall oxygen connection to an ETT, improper scavenger assembly, plastic wrap on soda lime, or a malfunctioning ventilator relief valve. The consequences can be pneumothorax, massive subcutaneous emphysema, cardiovascular collapse, and death.
The management algorithm for sustained high pressure is crucial. First, assess patient-related causes like bronchospasm. Then, try manual ventilation with the anesthesia breathing circuit in bag mode. If pressure is relieved, the ventilator relief valve is likely at fault. If pressure is sustained, the APL valve or scavenger is obstructed. In either case, consider disconnecting the patient from the breathing circuit and resuming ventilation with an ambu bag while assuring anesthesia depth via total intravenous anesthesia.
Finally, let's address the anesthesia workstation and malignant hyperthermia, MH. If an unexpected MH crisis arises, the protocol is clear. Immediately withdraw triggering agents, volatile agents, 6-no-choline, hyperventilate with 100% oxygen, and increase fresh gas flow. If time and help are available, change disposable breathing circuit components in granules.
Activated charcoal filters are a critical tool here. Easily applied between the inspiratory and expiratory ports and the breathing circuit limbs, they quickly and reliably reduce volatile agent concentration and are recommended by the Malignant Hyperthermia Association of the United States, MHA-US. When preparing for an MH-susceptible patient, change the breathing circuit and CO2 absorbent, disable or remove vaporizers, and flush internal circuitry. The old guideline was 10 lumen for 20 minutes, but new evidence shows this can be inadequate for some workstations, with the Fabius potentially needing as much as 104 minutes. MHUS now recommends a 90-second flush, adding charcoal filters to both limbs and maintaining high, fresh gas flow throughout maintenance.
That brings us to the final D of the SPDD model, disposal or managing waste anesthesia gases, WAG.
Scavenging systems are designed to collect waste anesthetic gases from the breathing circuit and ventilator and remove them from the operating room. A critical balance must be maintained. An amount equal to the fresh gas flow must be scavenged each minute. Otherwise, the breathing circuit and the patient's lungs will either gain or lose pressure, potentially resulting in barotrauma or failure to ventilate. The scavenging system has several components: a gas collection assembly at the ATL or ventilator relief valve, transfer tubing, the scavenging interface, which is the most important part, and the gas disposal tubing and assembly.
The Occupational Safety and Health Administration, OSHA, publishes advisory recommendations for exposure to waste anesthetic gases. They advise no worker exposure above 2 ppm for halogenated agents, 0.5 ppm if used with nitrous oxide, and no more than 25 ppm for nitrous oxide based on an 8-hour time-weighted average. Unscavenged operating rooms can have much higher levels, and while the direct harm from occupational exposure to halogenated agents is unproven, occupational exposure to nitrous oxide should clearly be avoided. Room ventilation, equipment conditions, scavenger effectiveness, and user anesthetic techniques all determine how much WAG reduction is attainable.
The scavenging interface is the most important component because it protects the patient's airway from both excessive positive pressure buildup and exposure to suction. There are two types. Closed interfaces, found on older workstations, communicate with the atmosphere only through valves. They must have positive pressure relief, releasing waste gases to the OR air if suction fails. And If attached to suction, must also have a negative pressure relief valve, drawing room air when suction is excessive, preventing patient or circuit gas from being emptied. Suction must be adjusted as fresh gas flow changes to keep the reservoir bag balanced.
Open interfaces, which are newer and most common, are open to the atmosphere. They have no valves, which makes them safer for the patient, as there's no risk of relief valve failure causing barotrauma or suction. However, they must be used with active suction systems. If scavenger suction is inadequate, all waste gases are released into the OR, potentially making them less safe for the unfamiliar operator. The smell test is a good indicator here. If you smell volatile agents during a case, it's abnormal, indicating an excessive concentration well above OSHA advisory levels.
Limiting exposure to waste anesthetic gases involves a proactive approach. Always check scavenger suction before use, perform regular preventive maintenance of both room ventilation and anesthesia equipment, and conduct personnel and ambient trace gas monitoring. If you smell anesthetics, seek the source. Maintain a good mask fit, avoid unscavengeable techniques, and prevent gas flow into room air. Example, pause fresh gas flow during intubation. Turn on anesthetic gases only after the mask is on the patient and turn them off before suctioning. Wash out anesthetics into the scavenger at the end of the case. Do not spill liquid agent. Use cuffed endotracheal tubes. Use low fresh gas flows. Check the workstation regularly for leaks and disconnect nitrous oxide at the wall outlet at the end of the day. Using total intravenous anesthesia or avoiding nitrous oxide altogether can also help.
Finally, let's explore risk management, the unseen shield of patient safety. At the department level, risk management is a detection system designed to predict failures and ensure precautions are taken to prevent patient harm. This includes activities like pre- and post-operative rounds, maintaining high standards of care, peer review, and continuing education. Equipment focus means cleanliness, daily performance of equipment checklists, familiarity with manuals, and appropriate maintenance.
The Safe Medical Device Act of 1990 requires hospitals to report instances where medical devices cause or contribute to death, serious illness, or injury. Problematic equipment must be removed and reported to the FDA. The most common barrier to investigation is alteration of the equipment cleaning, disassembly, or testing before a forensic evaluation. The best practice is to sequester equipment as is after patient injury. Equipment logs for each workstation are crucial, and preventive maintenance should be done 2-4 times a year by qualified, factory-trained technicians.
On an individual risk management level, your personal contribution to safety involves active involvement in the department-level plan, but also focusing on your workstation checklist before use, limiting disease transmission, and reducing WAG exposure through your work practices.
The Anesthesia Workstation Checklist, or PACASI, is truly the last line of defense at the point of care. Reports from the 1980s prompted the development of these checklists, because while equipment failures are rare, they are often due to human error. Failure to adequately check equipment has been implicated in up to 30% of critical incidents. In one study, 30% of checked workstations had serious faults discovered. Proper and consistent use of checklists not only prevents incidents, but also helps teach users how workstations function. It's associated with decreased mortality, and 1/3 of closed claims related to breathing circuits were judged preventable by an adequate PAC.
The new 2008 Pre-Anesthesia Checkout, or PAC, represents a significant shift in philosophy. It abandoned the 1990s FDA checklist because it didn't work for the varied modern workstations. This new checklist is a statement of principles: what should be checked, how often, and who should check it, rather than a rigid procedures list. This means departments must develop specific procedures and training for their workstations in consultation with manufacturers and manuals. User training is vital.
While electronic self-check routines on newer machines like the AZs, Fabius, Perseus, and Apollo help prevent errors and omissions, they can be incomplete or misleading. For example, some automated leak tests do not test for leaks at vaporizers. A loose filler cap or a leak at the vaporizer mount can easily be missed. Automated checkouts also require circuit occlusion for testing, followed by reconfiguration. Ideally, automated checkout should be transparent, clearly revealing what functions are checked, any deficiencies found, and recommendations for correction.
Ultimately, the provider is personally responsible for ensuring the anesthesia equipment is safe and ready for use. Technicians can assist, providing redundancy for critical steps like checking backup ventilation equipment. However, the clinician must learn each piece of equipment they use. While the PAC is essential, it recognizes that in emergencies, delaying care for a full checkout could worsen the patient's outcome.
Let's quickly highlight some specific items to check, focusing on the rationale. First, verify the auxiliary oxygen cylinder and a self-inflating manual ventilation device, AMBU bag, are available daily.
The rationale is that inability to ventilate is a major cause of morbidity and mortality. After checking the cylinder pressure, always close the valve to prevent silent depletion. Second, verify patient suction is adequate prior to each use for immediate airway clearance. Third, turn on the anesthesia delivery system and confirm AC power daily to prevent system shutdown when the battery backup exhausts. This is especially true for deslorane vaporizers.
Fourth, verify availability of required monitors and alarms prior to each use. This ensures you can conform to monitoring standards. Confirm proper function of pulse oximetry and capnography before induction by generating a capnogram yourself or seeing the patient's breathing efforts on the screen and checking audible alarms. Fifth, verify adequate pressure on the spare oxygen cylinder daily. Its acceptable pressure depends on its intended use and whether a pneumatically powered ventilator, which consumes oxygen, will be used. Close the cylinder valve after checking.
Sixth, verify piped gas pressures are 50 psi or greater daily, as minimum pressure is required for proper function. Seventh, verify vaporizers are adequately filled and filler ports tightly closed prior to each use. This prevents light anesthesia and leaks. Eighth, verify no leaks in gas supply lines between flow meters and a common gas outlet daily and whenever a vaporizer is changed. This requires turning on each vaporizer individually to check for leaks, as automated tests may miss them. Ninth, test scavenging system function daily to prevent OR contamination, checking connections, and adequate vacuum.
10th, calibrate or verify calibration of the oxygen monitor and check the low oxygen alarm daily. This is your last line of defense against hypoxic gas. Most require daily calibration, or self-calibrating ones need verification at 21% room air. 11th, verify carbon dioxide absorbent is not exhausted prior to each use, checking for color change or inspired CO2 greater than 0 on the capnograph. 12th, conduct breathing system pressure and leak testing prior to each use with the circuit configuration to be used, ensuring proper pressure development and relief via the APL valve. Automated tests are good, but still need manual verification.
13th, verify that gas flows properly through the breathing circuit during both inspiration and exhalation prior to each use. Pressure and leak testing don't identify all obstructions or confirm proper unidirectional valve function. Use the test lung or a second reservoir bag to confirm unimpeded flow and visible valve movement. 14th, document completion of checkout procedures prior to each use for accountability. And finally, 15th, confirm ventilator settings and evaluate readiness immediately prior to initiating the anesthetic. This is your anesthesia timeout to avoid errors from haste.
And crucially, there are user-performed checks beyond the electronic self-tests that are vital because many problems are not caught by automated systems. We recommend 4 vital steps to add. First, check the oxygen analyzer. Ensure it reads 21% room air and increases when exposed to oxygen pipeline gas. Second, check for backup ventilation, specifically an AMBU bag. Third, ensure the circuit is unobstructed and unidirectional valves are functioning properly by performing a flow test using a second breathing bag as a test lung. This detects things like mold flash, foreign objects, or plastic wrapping that automated checks might miss. And fourth, perform a high-pressure leak test on the reassembled breathing circuit. Release the pressure through the APL valve, which checks its function and propels any absorbent dust towards the scavenger, not the patient's elbow.
Even in emergencies, when time is limited, always check suction, essential monitor data, ECG, NIBP, SpO2, FiO2, capnography, your AMBU bag, and perform a high-pressure leak test of the breathing circuit before the mask is placed on the patient. And during pre-oxygenation, always take a brief moment to check the breathing bag for fluctuations. Visible respiratory effort in the bag before induction confirms the patient is breathing, the mask fit is good, and oxygen is flowing. Any absence requires immediate attention.
So what does this all mean? We've unpacked the incredible complexity and vital importance of anesthesia workstations, from the precise control of gases and agents to the sophisticated safety systems and the critical human element. Every detail contributes to patient safety. Mastery in this field isn't just about knowing the dials, it's about understanding the entire system, its vulnerabilities, and your indispensable role in mitigating risks.
This raises an important question. In an era of increasing automation and complex technology, how do we ensure that our reliance on machines doesn't erode our fundamental vigilance and critical thinking? The goal is for our patients to truly sleep in safety, a level of care that demands continuous learning and commitment from every professional. This deep dive is just the beginning of that journey for you.
Stay curious, stay informed, and never stop questioning how we can make tomorrow even safer than today. Until next time, keep diving deep.